Okay, this is one session on CAM, computer aided manufacturing. We will start this session by this question: how to prevent tool cutting in the wrong part of the workpiece. We have two choices. The first one is to use the G code, either 41 or 42. This option can be applied whenever the machine control unit can support this option. In case we don't have this facility, we can select the second option, which number 2, to shift the cutter location by certain amount, dx and dy, either in x direction or in y direction. When we can go for second option, we can go for second option whenever the machine control unit does not support the G41 and G42 code. Another situation where we have to go for that option, whenever we have a very intricate or very complex part, the part is very complicated, which may present a sort of complication to the machine control unit. And as a programmer, you have to solve this by yourself and get the job done by using this traditional programming method, which is to shift manually or by calculation by yourself to shift the cutter location by dx and dy amount. So how we can use this second method to shift the cutter location by certain amount as a corrective amount, dx and dy in x or y direction. Let us take some common cases for doing this step. The first case we have here is the workpiece. Whenever the workpiece has an acute angle, this is the workpiece and this is the acute angle. This is the two edges of the workpiece, and the cutter has to be moved to in a path or in certain direction to avoid that wrong cut in the workpiece. How we can achieve this objective? First of all, we have to shift the two edges by the same amount of the cutter radius. So we create these two lines. This two line is created by shifting the workpiece edge to get the first line, and the second workpiece edge will be shifted to get the second line. So the intersection of these two lines, we locate that intersection, and then we connect that intersection, which considered now as an alternative to the original workpiece edge. So we connect these two edges. This is the intersection, the first intersection or the real intersection of the workpiece, and this is a virtual new intersection of the path location or the path route. So we join these 2 points and we try to create a right angle on that line. And that shadow triangle is the angle we are looking for. We are after that line. This is our interest, is to look at this right angle triangle. The intersection between the 2 points represent the chord of that triangle, right angle triangle, which has a right angle here. We have to solve that triangle. What I mean by solving, to know at least to know 2 sides of that triangle, because normally these 2 sides represent the amount of shift we're going to use in avoiding that wrong cut in the workpiece. So as we see in that triangle, the first side of the triangle actually represent how much we shift the cutter in y direction, which is dy. That is straightforward equal to the cutter radius. It is equal to the cutter radius. So dy here is directly equal to the cutter radius dy. The second shift is dx, which is that amount. That amount represents the amount we shift the cutter. We shift the center line of the cutter from being here at that edge to that new edge location. So this is the amount we shift from that point to that point along the x-axis. This is the dx. So the amount of dx will be calculated by applying some trigonometrical relationship along that right angle triangle. So assuming we have the workpiece with an angle theta, assuming this angle is equal theta, whatever the value of theta, of course it is acute angle, so it is less than 90 degrees. So as far as it is less than 90 degrees, we apply this case. So this case is applied for whatever angle is than 90 degrees. So if this is theta, so that angle is the same. That angle will be again equal theta. That angle equal theta. So that since these two triangles are equivalent, so that angle will be half of theta. So this one half of theta, theta divided by 2. So this triangle, this shadow triangle, what we know one angle and we know one side. So after we need to know the second side, which is in that case d delta y or dy, dx. We need to know dx. So dx is that side. So simply if we apply one of the trigonometric relationship, tan this angle will be this value divided by this, the opposite divided by the adjacent. So dividing dy by dx equal tan theta or tan half of theta. So since we know theta, we should know theta, of course, because we know the geometry of the workpiece. And we know that this opposite side, which is dy equal the cutter radius, assuming the cutter diameter is 0.5, so the cutter radius will be 0.25. So if we know the cutter radius, that should be the cutter radius r, and we know the angle, so it is very easy to now to estimate the amount of dx. Dx will be cutter radius r divided by tan theta over 2, or tan half theta. So based on the value of theta and based on the value of r, we very easily calculate dx. As a special case, if that theta is equal 45 degrees, for example, if it is 45, but of course it's not necessary to be 45 degrees, it could be any value less than 90 degrees. So if we apply, and if we know the radius equal 0.25, in that case, if we apply this trigonometric relationship, we are able to get dx straightforward. So based on this calculation, the cutter has the cutter center point, this is the cutter center point, has to be shifted from the edge corner under consideration. This corner is under consideration. So the cutter has to be shifted from the center of the cutter, has to be shifted from the workpiece corner edge by a certain amount in x direction, which is this amount, and by a certain amount in y direction, which is equal to the cutter radius. The second case, if we have obtuse angle. Obtuse angle means that theta is more than 90 degrees. So this is the second case. This is greater than 90 degrees. The treatment is almost very similar. What we have to do, we have to shift the two edges of the workpiece. This is the first edge, we shifted to that line. And we shift the second edge to that location. The amount of shift is equal to the radius of the cutter. So this is the radius, this is the amount of the shift equal to radius of the cutter, R. These two lines will intersect at certain point. This is a virtual, this actual cutter center location to avoid wrong cut in the workpiece. So that point, we join it to the edge of the workpiece by a certain straight line. This is a line. And we use that line as a chord to create a right angle triangle. And the right angle triangle we try to create on that line will be the chord of that right angle triangle. The other two sides will represent dx and dy. So as we see here, this is the other two edges of the right angle triangle. This is the right angle triangle. As you see here, one side again represents dy, which in our case will be again the radius of the cutter, and the other value will be again dx, which is the amount of the shift of the center of the cutter from the edge of the point by this amount. So again, if we know this angle of the workpiece, so half this angle will equal this angle of the right angle triangle. So that angle will be again half theta. So if we apply this equation, trigonometric equation, what is the tan of this angle? Tan will be the opposite divided by the agent h. So tan theta divided by 2 equal to that opposite h, which is r, divided by r is known, divided by this amount which is del dx, which is unknown. So we know, if we know theta and we know r, so it is very simple and very easy to get the amount of shift along the x direction. So again, this is the second case. We magnify the location of the cutter. This is the edge of the workpiece, and this is the center of the cutter, and this is the line which we use to join the two points. This is the right angle triangle. This is right angle. We are interested in these two sides. One side is equal dx and the other side equal dy. dy is known equal r. Using this trigonometric relationship, we get delta dx. For example, if the workpiece angle as a special case, or as an example case, if this angle is, say, 110, so half the angle will be 55. If the cutter radius is again 0.25, so tan half of that angle will equal r divided by dx. Then we can very simply get dx, which is that amount, and the dy is the cutter radius. So if we shift the center of the cutter from the edge of the point with this amount in the x direction, this is the x direction, we shift it to that amount in the x direction, and we shift it to that direction with this amount in the y direction, then it means we locate the cutter. Instead of the cutter being located at that point, we will shift it to the center to that point, so that will be the new cutter location. If the cutter now is traveling along this route, along this path, it will never do any wrong cut in the workpiece. This is our workpiece. So we avoid any wrong cut in this shadow area. As we see here, this is acute, this is obtuse angle, more than 90 degrees. And again, this obtuse angle can come in different configuration. For example, one edge here is in line with the x-axis. So this is the x-axis, and this is the y-axis. We see that workpiece, it comes like this, just, it could happen like this. One of the edge is parallel to x-axis. Let us take another case, the same obtuse angle, but the one edge is parallel to y-axis, like this case. One edge of the workpiece now is parallel to y-axis. Again, this is the x-axis, and this is the y-axis. This is the difference between the third case and the second. Only change in the geometry of the workpiece. So the two edges of the workpiece, again, it has obtuse angle bigger than 90 degrees, but one edge of the workpiece is in line with the y-axis. The previous case, it was one edge was parallel with the x-axis, but here one edge of the workpiece is in parallel with the y-axis. This is how the cutter is supposed to move. It's supposed to move like this, like this. It's supposed to be like this. So this is the animation of the cutter movement. So it has to move in that path. To get the cutter to move in that path, we have to shift again the two edges as we proceed before. One shift parallel to the first edge, and another shift parallel to the second edge. The two shift lines will intersect at a point. Again, that point will represent the center of the cutter to avoid wrong cut in the workpiece. Again, we connect these 2 points, and that line will represent the chord of right angle triangle. So we try to create 2 right angle triangle. That below one is one of these triangle, that one. And again, most of the time you will find that one edge of the right angle triangle represent dx or dy, and it is equal to the cutter radius. In our case here, that represent dx, and the dx here equal r, so that amount equal dx. So dx directly equal r. If we know the cutter radius, then dx equal r. Back to this below triangle, try to solve that below triangle. What you know about this triangle? Again, if you know this angle is theta, so that angle equal half of theta. So again, apply the same trigonometric relationship. Tan this angle, tan half theta, equal the opposite, which in our case r, divided by the adjacent edge, which in our case is dy. So the opposite is dx, and the adjacent is dy. So tan half of the angle equal the opposite, which r, divided by the adjacent, which in our case is dy. What is known here? We know theta, we know r, so what is unknown here will be dy, so we can easily get that dy. Very similar to what we done before. Case 1 and the case 2 and the case 3, all the movement of the cutter are along straight lines. It go along straight lines. What if the workpiece initially has a circular or curved segment along its geometry, like we have here? This is case number 4. The workpiece initially has that curved sector. It has a segment along the shape of the workpiece, which has that circular segment. For any circular segment, we treat the case in different way. How we treat it? We all the time refer to the center of the circular segment. So try to trace to locate the center of the circular segment. So this is a circular segment. This is the center of that circular segment. And the dx and the dy will refer to that point. For example, if this is the location of the cutter, in that case we have two locations. Actually, we have to solve the cutter into two positions. We have, of course, the position number one, the cutter, if the cutter coming from that direction, we call this position number one, and the position number two, and the position number three. Now we are not concerned about position number one. It is very easy and simple to treat position number one. Let us look at position number two. Assuming this is the position of the cutter, how to find the location of the cutter center to avoid wrong cut in the workpiece? That should be the location of the cutter. How to refer that location to the center of the curvature? In that case, if this is the triangle, this is the triangle we consider. What we know about that triangle? We know that chord, which is equal the radius of the curvature of the workpiece plus the radius of the cutter. So that will be R of the workpiece plus R of the cutter. And of course, we know that angle. We should know that angle. It should be known from the geometry of the workpiece. So this is what we know. We know the cutter radius. We know the workpiece radius, for example, 2. So if we add 2 plus 0.25, we will get that length. If we get that length, then, and we know that angle, then we easily can find the shift in x direction and the shift in the y direction referred to the center of the curvature. That should be the root of the cutter, and it should go through that route. Now, in our case, dy is given. So sine this alpha, this angle, assuming this alpha is a or whatever, theta or alpha or a, whatever. So sine this alpha will equal this amount divided by this amount. So we know this given here as a given data. So we know that opposite side, and we know that length. So we can get alpha or e, whatever this angle. Once we go the value of this a, then we can use it to get dx. How we can get dx? Just apply the chord cosine this angle. So if we know the alpha should be equal dx divided by dy. So in that case, we can very simply, we know alpha, we know dy, so we can very simply get dx, which in our case will equal this amount. What about the position number 3? We solve for position number 2. Now, what about position number 3? It is very similar. The connection between the cutter location and the center of curvature, we know that length. And we create that right angle triangle. Why we create that triangle? Because that two sides of that triangle represent the shift in dx, the shift in x direction, which is dx, and the shift in y direction, which is dy. It is very similar to the position number 2, but here we use this total angle. This total angle actually include whatever we already calculated, a, plus this amount, and this amount is given here as a data. So if we know that angle and we know that chord, So that chord cosine that angle will give us dx. And again, that chord sine that angle will give us dy. This is what we're going to apply here. So we're able to get dy and we're able to get dx using that sine and the cosine relationship. Now we have many special cases. We consider these cases, and now we can get a real application. Assuming this is a real application, this is the geometry of the part we have. Then we can use the dimensions given in that part to calculate the cutter positions starting from that point. Of course, the cutter should start from here. So this is the position of the cutter initially. It should be like this. This is the center of the cutter. What is required to find how shift the center of the cutter from point number 1 to avoid wrong cut in the workpiece. For that point, it is very simple. The shift here will be in x direction, will be the same as y direction. It will be the radius cutter, radius, the radius of the cutter. So that will be dx, which is equal here equal minus r. R is the cutter radius. And again, this is dy. dy again will be minus the cutter radius. So dy will be minus r. Why minus? Because you shift the center from referring to that workpiece corner. So assuming that workpiece corner is the location of your x and y coordinates, assuming this x and this y. So the original of your coordinates passing by the workpiece edge. So how we will locate the cutter center from that point? It is in the negative direction of x, and it is in the negative direction of y. That's why dx is minus and the dy also is plus. When we come to point 2, we will apply the obtuse example, because this angle now, obtuse angle, greater than 90 degrees. So we apply very similar to case 3 we mentioned before, to that case we mentioned before. Yes, very similar to that case 3. So that case 3 will be applied to that point, to that position. And case 2 will be applied to point 3, and so on. Most of the cases will be almost the same. Some dimension might not be included here, but you can get it from something like that, or we can simplify this case, make it more simple, or make it symmetry. So instead of using that workpiece, you can go for that one. It is more easier than that one, if you like. When we mention that dimension, what we mean by that dimension, for example, when we point to that side, 0.75, we mean that that is a chord of equal angle. So that one and that one, every side is equal 0.75. This one is not equal 0.75. This is the one which is equal 0.75. This I just have to mention that. Again, for that one, when we point to that edge as 0.5, it doesn't mean that chord is 0.5. What we mean that this is 0.5. These two sides equal 0.5, and so on. So that point 2 is very similar to case 3 as we mentioned before. It will be something like that. This is the situation. This is the location of the cutter. It should come here. This is the root of the cutter to do that, avoiding that wrong cut in the workpiece, and you have to solve that below triangle as we did before when you deal with that point number 2. And for point number 3, it is very similar to that case, which case number 2 we mentioned before. It is very similar to that case. You have to solve that black triangle when you deal with that point number 3. Point number 4, when you come to point number 4, this is a triangle, this black triangle again, the one you have to look for, and that dy will be will equal to r. And that angle, if that angle is A, so that angle is half A divided by 2. So in that case, you can use tan this angle will equal r divided by dx, and that will be dx. So you can very simply get dx. That will be dx. For point number 5, that is point number 5. This is how to deal with that point number 5. Again, this is a two-line shift, shifted by r, cutter radius, and that again also that line also shifted by the same amount, cutter radius r. So we get the intersection of these two lines, join that line to the edge of the workpiece, create that black triangle, right angle triangle. Make sure that the triangle you create include both dx and dy. One side will equal dx and one side dy. In that case, which side is equal dx? That one equal dx, and in that case, it will equal directly equal to r, the cutter radius. And again, that one has to be calculated using either sine or cosine or tan, whatever the situation. So in that case, if we know that angle equal half that angle, so in that case we can apply tan. Tan A divided by 2 will equal dy, which equal r divided by dx. In that case we can get dx. Again, point 6, very easy and very simple. If we locate the cutter, it will be located like this. As we see here, this is the location of the cutter. And this is the center of the cutter. So in that case, if the cutter radius, for example, whatever the cutter radius, if the cutter radius is 0.25, so in that case, dx will be 0.25. If the cutter radius is 1, so dx will be 1. And the dy will be equal 0. Will be equal 0. dx here will be positive. Will be positive. That one will be plus 0.25. And dy will be 0 because no shift between the workpiece edge and the cutter location, center location in the y direction. They are located on the same x direction, so there is no shift in the y direction, only shift in the x direction, and that shift in the x direction equal the cutter radius. If we refer that, if we use our recommendation before that, whenever we have a curved shape, this is the curve of the workpiece. In that case, we will treat the situation in different way. Instead of using dx equal 0.25, in that case, we will use some another alternative. Let us see the another alternative, which it is preferred actually to use that alternative. In that case, instead of referring the cutter location to the edge of the workpiece, we refer to the center of curvature. So if this is a curvature and this is center of curvature, we have to locate, we have to refer the cutter location if this is our cutter. So in that case, is better if we locate the center of the cutter to the center of curvature. So that in that case will be dx instead of our previous treatment. So that will be dx. Okay, so if the radius is 1.25, as we see here, this is the curvature of the workpiece 1.25, and the cutter radius is 0.25, so in that case delta x will be this amount. What about this amount? What is the value of this amount? This is in that case will be dx. So in that case dx will be again minus 1. How we get that one? This is 1.25 minus the cutter radius, so that is dx minus 1. What about dy? dy again equal 0. So we can use these figures in if we refer the cutter location to the center of curvature of the workpiece. What about point 7? This is point 7. This is along the workpiece edge, and this is the edge of the workpiece which in tangent with the curvature of the previous segment of the workpiece. So again, refer to the center of curvature. This is the center of curvature. In that case, so if we know this angle, we will see how to know this angle. But assuming we know that angle alpha, we are interested in that right angle triangle. Again, very similar to what the procedure we followed before. This is our cutter. This is our cutter location. Refer to cutter location to the center of curvature. This is the workpiece curvature, and this is the center of the curvature. This is the curvature radius, which is 1.25. So we know the distance between the center of curvature and the center of cutter, which in our case will be the curvature radius minus the cutter radius. So that chord will be curvature radius minus cutter radius. Assuming we know that angle, and using that angle and that chord, we can create again that right angle triangle. And whenever we create any triangle, we keep in mind that two edges of that triangle represent the two shift. So that edge will represent dx, and that edge will represent dy in our case. So if we know alpha, if we know that angle, and we know that chord, which is r capital minus r small, so r capital minus r small cosine alpha, assuming we know alpha, that will give us dx. And again, dy, which is that one, will be r minus r sine alpha, so we able to get dx. How we know that alpha? We know that alpha if we know the slope of that workpiece. This is one sector along the workpiece. Back to our geometry of the workpiece we have. This is the workpiece. This is the edge. If we know that angle, if we know that edge slope, we know that angle. For example, theta. So we know 180 degrees minus theta will give that angle. So we know that angle. Okay. Once we know the slope of that edge, which should be given as part of the workpiece geometry from the dimensional given on the workpiece, we able to get that angle. So once we know that angle, which is the slope of that edge, we able to get the complement will be the other angle, and that angle and that angle are similar. They both are similar. They both the same. So again, that will be that one and that one will be similar. So if we know the slope, theta or alpha, so that angle will be again the same. Or if we know that one, we get the complement, and the complement will be equal to that one. So very simple to calculate dx and dy. This is our session, and we will continue in the remaining cases in the next video. Thank you.